So remember the linear regression model? It had two unknown parameters, beta 1 and beta 2. And the main point was trying to estimate these beta 1 and beta 2 given the observed data. Well, it turns out that this is kind of a hopeless task unless you make some additional assumptions. And the key or most important assumption which will allow at least some sort of success is the exogeneity assumption. So this lecture will be all about explaining what we mean by an explanatory variable being exogenous. And with this assumption, we can go ahead and estimate the unknown parameters. So the linear regression model assumed that the relationship between yi and xi was as follows. Yi is partly determined by a linear function of x and partly determined by the error term epsilon I. And I have this random sample which I want to use to estimate beta 1 and beta 2. So I brought it over here. Let's consider the conditional expectation of yi given xi. So the expected value of yi conditionally on xi. For a concrete example, let's again think about xi as being the number of hours a student studies and yi the result on the final exam. The expected value of yi, well, that's the expected value for all students, while the expected value of yi conditional on xi, that's the expected result for a student that has studied precisely this many hours. So we would expect this expectation to depend on x. And indeed it will. If I just replace my yi in here, this is expected value beta 1 plus beta 2 xi plus epsilon I conditionally on xi. Now we have plus signs here, so this is a linear function, which means that I can break this expectation up into three parts. So I can write it as expected value of beta 1 conditional on xi plus expected value of beta 2 xi conditionally on xi plus expected value of epsilon I conditionally on xi. For the first part, the expected value of beta 1 conditionally on xi. Just remember that beta 1 is a parameter. Even though it's unknown, it's still just a constant. So knowing the number of hours a student has studied is not going to change that. The expected value of a constant is still just a constant, even though we condition on something. So it's going to be beta 1. For the next part, the expected value of beta 2 times xi given xi. So that's like saying, what's the expected value of beta 2 times xi if I know that xi is, let's say, 120? Well, if I know that xi is 120, if I condition on that, then beta 2 xi is no longer random. It will be a constant in that case. So the conditional expectation of beta 2 xi given xi is just beta 2 xi. And then we have the final term. In general, we can't say anything about the expected value of the error term once I know xi. And this result is true for all observations. So bringing this back, we have the following result. The expected value of yi given xi is this same linear function of xi, beta 1 plus beta 2 xi, plus the conditional expectation of the error term. So let's think a little bit more about this part here, this is kind of a key component in the linear regression model. The error term, remember, contained all the stuff that affects yi in addition to xi. This is the expected value of all that stuff for a given value of xi. So if we assume that this expected value is 0, then we're basically saying that no matter what the value of xi is, no matter how many hours students have studied, the expected value of the error term is 0. Meaning that for some individuals, the error term is positive, for some individuals, the error term is negative, but the expected value is 0. One of the key points here is that this expected value needs to be 0 no matter what the value of xi is. So we cannot allow the error term and the x variable to be correlated. Remember, if the error term and the x term is correlated, then the expected value of epsilon I given xi cannot be 0. Then the expected value of epsilon I will depend on xi. For example, if they're positively correlated, then the expected value of epsilon I will be greater when x is large and smaller when x is small. So to summarize these things, if this last term is 0, then we say that the x variable is exogenous. If the expected value of the error term given xi is 0, then the x variable is exogenous. The error term, they all affect the y variable, but the point is, for some individuals the error term is positive, for some individuals it's negative, but on average it's 0. We know from a previous lecture that if these two terms, epsilon I and xi, are independent, then this will definitely hold. So if the explanatory variable and the error term are independent random variables, they have nothing to do with each other, then the x variable is exogenous. Unfortunately, the independence assumption is typically a little bit too strong in econometrics. And also unfortunate, it's not enough that the error term and the x variable are uncorrelated. So this exogeneity assumption, you can think of it as an assumption just somewhere in between independence and uncorrelatedness. It's stronger than uncorrelated, but not quite as strong as independence, and it turns out to be precisely what we need for our estimator of beta parameters to have nice properties. So if the explanatory variable is exogenous, then this final term is 0, and then we have the following result. The expected value of yi given xi is equal to the first part of the linear regression model. So with the exogeneity assumption, this part here is the conditional expectation of yi. If x is exogenous. And you can equally well define exogeneity as this relationship holding. So you can also define and say that x is exogenous if this is true, because it's exactly the same thing as this being equal to 0. So what we're saying with the exogeneity assumption is really this in terms of the example. A student that has studied this number of hours should expect to get a grade on the final exam which is a linear function of that many hours. Of course, doesn't mean that that's exactly what will happen. It just means that that's the expected value. Exactly what will happen is this term plus a random error term, but that random error term is 0 on average. So another very useful notation from the linear regression model is that we can specify this part as the conditional expectation if the explanatory variable is exogenous. So we can simply write the linear regression model then as the actual and the value of yi that we will observe is the conditional expectation, what we would expect from a student having studied this many hours, but it's not going to be exactly that. It's going to be that plus some error term. And this is also a very useful way of looking at it. If I move this term to the right hand side, we can actually see what the error term is in the case of exogeneity. So when the explanatory variable is exogenous, the error term is simply the difference between what we observe for yi and what we would expect to observe for yi. So in that sense, it indeed is really an error term. What we observe minus what we would expect to observe. And that's a very useful way of thinking about the error term in a linear regression model. So just collecting these results in the presentation. If the explanatory variable is exogenous, we know that this is true. Then the conditional expectation is just a linear function of the x variable. That means that I can decompose the observed value of yi into the expectation part and the error part. And that in turn means that I can write the error part as the difference between the observed and what we expect to observe. The exogeneity assumption also allows us to really fully interpret the beta parameters. But first, let's just note the following. When we make the exogeneity assumption, when we say that the expected value of yi given xi is this linear function, then we say that this holds true for our sample. So the expected value of y1 conditional on x1 is beta 1 plus beta 2 x1 and so on. But we really think that this will be true for an arbitrary value of yi and xi. That is, if I look at another student which is not in my sample, then I would still think it's true that the expected value of the exam result, given the number of hours studies, is exactly the same linear relationship. So we typically extend this view to go beyond our sample. And whenever we look at an arbitrary value of x and y, not necessarily a point in the sample, then we simply remove the subscript I. So for an arbitrary x and y value, we just call it x and y, then we'll write exactly the same thing but without the subscript I and without the I go from 1 to n. So this would be the exogeneity assumption for an arbitrary observation. Well, as you know, the linear function on the right hand side, beta 2 is the slope. So we can always then interpret beta 2 as a derivative. If I differentiate the left hand side with respect to x, the result will be precisely beta 2. And that is the interpretation that we will have for beta 2. So the linear regression model plus the exogeneity assumption implies that beta 2 is the derivative of the conditional expectation with respect to x. So beta 2 really answers the following question. If I increase x by 1 unit, how much will that increase the conditional expectation? In terms of our example, if a student studies 1 more hour, how much will that increase the conditional expectation of the result on the final exam? We can only state things in terms of expected value because we don't really know what's going to happen with an individual exactly, since each individual has its own error term. But on average, the result will increase by an amount which is exactly equal to beta 2. In some books, this is then called the marginal effect of the x variable. But you have to be a little bit careful with that notation. I'm not too fond of it, simply because when we talk about the marginal effect of an explanatory variable, what we mean then is that I increase the value of this variable by, let's say, 1 unit, while keeping everything else the same. Beta 2 doesn't really answer that question. Beta 2 in the linear regression model with just this one explanatory variable just answers the question, if I increase x by 1 unit, what will happen to the y value? I'm not keeping everything else the same. Another thing I want to point out is that it's quite common to start from the linear regression model, differentiate this with respect to xi, to do the yi, the xi, and say that this doesn't depend on xi, so that becomes 0. The derivative of beta 2 times xi, that's just beta 2. And to say that the derivative of the error term with respect to xi is 0 as well, and then to claim this one, which is different from what we said. We said that the derivative of the conditional expectation, the xi, is beta 2. There are actually many reasons to avoid this kind of notation. First of all, this derivative of the error term with respect to xi is just not really a well-defined concept. It's hard to say what we mean by the derivative of an error term with respect to an explanatory variable. Second, it's also an interpretation question here, because with this interpretation here, what we're saying is that beta 2 is the actual increase in yi when xi increases by 1 unit, which isn't quite correct. It's only correct if you assume that the error term is the same, if the error term for that particular individual is the same. It's much more, even though it's a little bit more difficult to interpret, but it's much more correct to think of this parameter beta 2 as the derivative of the conditional expectation. It's the effect that xi has on the average value of yi, rather than the effect that xi has on the actual value of yi that beta 2 measures. So we'll avoid this notation completely, even though we can appreciate that perhaps for a beginner it might actually be a more useful formula. We can also interpret the beta 1 parameter, the intercept. Remember, we have this relationship, which is key. So what we can see here is that if I put xi equal to 0, then I have beta 1 on the right hand side. So beta 1 is simply the expected value of yi for xi equal to 0. So that's this one, the expected value of y for an arbitrary observation given that x is 0. In our model, it would be the expected result on the final exam for a student that has studied nothing. It's really important here that we view it as the expected value, because the actual value, well, that will depend, it will be different from student to student. Some students that have studied nothing will do better than other students that have studied nothing. Beta 1 measures the average result among students who have not studied at all. So let's just re-emphasize this. The important parameter in the linear regression model is beta 2, because in economics we're typically interested in the effect on this conditional expectation when x increases, not so much in the intercept. So here is the main point, or the important part of this lecture. If you have a linear regression model and you make the exogeneity assumption, it's really important that the x variable is exogenous. Well, in that case, you can interpret this beta 2 parameter in the linear regression model as the increase in conditional expectation when x increases by 1 unit. That's what makes beta 2 so important, because it's precisely these kind of questions that we tend to ask in economics. Questions such as, if an individual has one more year of schooling, what's the increase in the expected income from that? That is, how much does an individual gain in income per year, say, by doing one more year of school? Or we could look at, what's the expected decrease in demand of a good if we increase the price by 1 unit? What's the expected change in the total revenue for the government if we change a parameter in the tax system by 1 unit, and so on and so forth? We are often interested in derivatives of conditional expectations with respect to various